So, work energy theorem and the law of conservation of mechanical energy go hand in hand. Okay? What's different is that in work energy theorem, there is a difference between the initial energy and the final energy, and whatever that difference is represents the work in or out of the system. In a perfect law of conservation of energy situation, the initial energy and the final energy are equal. Therefore, no work has gone in or out of the system. Okay? Now, is there ever a situation where this is perfectly true? Not ever. Okay? There's always going to be some energy lost in any energy conversion. That's what the lab we did last week is all about. Okay? Even in a simple energy conversion, like the cart going from the top of the ramp to the bottom of the ramp, a significant amount of energy is lost. Okay? Sound, heat, all those other things, they're always there. Right? And so they're always taking mechanical energy away. It is impossible to have an isolated system where the law of conservation of energy is always perfectly obeyed. Okay? Now, the law of conservation of energy is, of course, always obeyed. It just means not all of the energy ends up being mechanical at the end. Some of it is lost to sound, heat, light, and other forms. All that energy is obviously still accounted for. It's just not all mechanical anymore. Okay? But we're going to imagine perfect utopian physical world situations for this particular concept. Okay? All right, so first thing, energy cannot be created, it cannot be destroyed, but it can be turned into other forms that make it look like it. Okay, so if we got a roller coaster, which is the Science 10 example, okay, obviously in the real world it's not going as fast as it should be going in the perfect physical world because energy is going to be lost to sound and heat, etc. Okay, but energy is always conserved in some form or another. Okay, and so that leads to the second point: energy can be converted from one form to another. For conservation of energy problems, we're just converting potential energy into kinetic energy and kinetic energy into potential energy, and it's always being conserved. Okay, and so we'll be using that in some problem solving, exactly like what you would have done on a roller coaster question in Science 10. Okay, that's what we'll be going over today, right? And should seem pretty familiar. Okay, so there's two kinds of energy, kinetic and potential. It is their sum that is the mechanical energy of an object. Okay, that's something that we learned in Science 10. We talked about it already in this unit with work energy theorem. Okay, your total mechanical energy is your total kinetic plus your potential. Okay, that gives you your mechanical energy. So it's possible for you to have kinetic or potential or both, but you always have mechanical if you have either one of them. Okay. All right, this is what we learned about, or what we were working on last week. This is work energy theory. The work done against non-conservative forces is your final energy minus your initial energy. Okay, if there's a difference, then there was work done. Everyone okay with that? What we're going to be dealing with today is this. They're equal. There's no work done against non-conservative forces. Okay, so if that was the case, if you had a roller coaster that existed in an isolated system, would you ever be able to get off? No. Because it would just keep going. Okay, you tow it to the top of the first hill, let it go, and it would go forever, which would result in a lot of vomiting, probably. Okay, because nobody would ever be able to get off unless they could apply the brakes. That would be work done. Okay, so it would just keep going, which would be really, really weird. Okay, because the only sound from that roller coaster would be the screaming of the occupants. The roller coaster itself couldn't possibly make any noise because that would represent energy lost turned into sound. Okay, it would never get hot because that would represent energy lost. Okay, this roller coaster would be perfectly silent, other than the screaming of its occupants. Okay, which would be really, really strange. If you've ever gone, like, Callaway Park or West End, and you've been near the roller coasters, they're loud, and it's not because of the people on them. Okay, the roller coaster itself is loud. Okay, the wheels, the track, all of it makes a lot of noise when it's in motion. Okay, you guys following where I'm going with that? Okay. All right, so if we've got a roller coaster at the top of the first hill, it would be moving. You rarely have a roller coaster that's stopped at the top, okay? Although some do it just to mess with you. Okay, I'll show you a video. I think I have a video of one where it's a floorless roller coaster, so you're like, your feet are hanging out, and it leans you over the first hill and it stops you. So you're looking down like this, okay, at your doom. The Mindbender has done that at West Edmonton Mall. It did it to me and Mr. Dickey and a couple of our students one time on our physics trip that we no longer do. Okay, but it just went over that first hill and then the brakes came on. And we sat there looking at the first drop. For what seemed like an eternity, it was probably only 5 minutes, but it seemed like a really long time because nobody told us what was going on. The roller coaster just stopped. And you're like, well, this isn't cool. Okay. It was so not cool that the kid who was in the seat beside me was pulling a full-on Harry Houdini. Okay. Like he was getting off. He's like at the seat belt, and I'm like, I thought he was gonna like pop his shoulder out to get out from under the harness. Like he was literally trying to go full Mel Gibson and get out from underneath there. And I'm like, what are you doing? I'm getting out. Like, take a look around you. Where are you gonna go? Like, what? You're gonna just like along the side of the cars? You're gonna fall and die. Just sit still. You can't get out anyway because it's all attached, and it locks into place.
We don't do the trip anymore.
It has become cost prohibitive. We used to get a pretty good deal, and we could get everybody there for less than $50 a person. Now it's like 80. It's just not worth it to go anymore. So yeah, it costs too much money.
What about Callaway Farm?
Well, it doesn't run when we do.
Well, I guess it's the winter time.
Yeah, it's the winter now, right? I don't think you'd enjoy it today.
I really think about that.
All right, so at the beginning, we got lots of potential, very little kinetic. If we get to that lowest point, that would be where our potential energy would be at its minimum, or if it's ground level, would be 0, okay? And our kinetic energy would be at its maximum, right? And then you've got your, if you go up onto a little hill, you'd have a little bit more potential energy, a little less kinetic energy. But the point here is that they're constantly being converted into each other in a perfect system. Okay? You do the work to tone to the top of the first hill, and after that, the potential turns into the kinetic turns back into potential, up and down, up and down. Okay, so if that's what's going on, what's happening to the total mechanical energy at any point? It stays the same, yeah. So in a roller coaster, even the roller coaster is going up and down like this, okay? The total mechanical energy is a flat line. It's never changing. It's always the same number of joules. All that changes is how much is kinetic and how much is potential. If we had a graph of how much was kinetic, it would do this. Okay? If we had a graph of how much it was potential, it would do this. Okay? But a graph of total mechanical would be flat. Yeah, wouldn't change. All right. So in other words, the final mechanical energy in any true conservation of energy is equal to the initial. Okay? And so we can simply say EI equals EF. Okay, that would be stating the law of conservation of energy mathematically. All right, and so if we were going through this, okay, up here, lots of potential, very little kinetic. Okay, as we go down, this would be our maximum kinetic right here. Okay, and then we go up, we'd have some potential, some kinetic, turning back into kinetic. Okay, going up again, so we'd be all kinetic down here. Going back up into the loop, converting some back into potential, then turning it back into kinetic, getting to our maximum. Okay, going up a little bit, we'd have a little bit more potential, a little less kinetic. Okay, maximum kinetic, a little bit of potential. Okay, mostly kinetic, back to maximum kinetic. Okay, throughout that whole thing. Okay, but the sum of those two numbers is always the same at any point on that track. Okay. All right, so now, I mean, at this point in the course, you know I'm like full nerd, okay? And I'm okay with that. I know who I am, and I'm comfortable being like full nerd. I used to coach track and field, and I saw this thing at provincials one year. I know, see, that's the reaction everybody else had when I got the whole team, you guys gotta come see this! And they look at it like, it's a ramp. No, it's more. It's so much more than a ramp. Because it had been designed so that if you placed a shot put, regardless of which one it was, the men's, the women's, the juniors, the seniors, whatever, okay, if you put it at the top of that ramp, it would roll down. That's not the exciting part. Okay? But as it would roll along this level part, what would happen to its energy? It would decrease because of friction. They had figured out how long to make this based on how much friction there was between the shot put and the ball, so that when it got to the end of the track, it stopped. And there wasn't a divot to catch it. It wasn't like at the bowling alley where that flap is there, you know, and the kids always get their fingers smashed in between the balls. Okay? This thing would actually literally stop right at the end. It would just coast to a stop. Didn't matter which ball you put. As long as you set it at the top and didn't like give it a push, it would stop at the end. Okay? I watched it a bunch of times before I got really excited and brought the whole team over to show them. And then they're all like, you are such a nerd. And I'm like, yes.
That's actually kind of awesome.
It is kind of awesome. I'm glad you see it my way.
What's the
Okay?
function of it? Like why?
It's just to return the shot puts.
Oh.
Rather than have that, because they're hard to carry. They're quite heavy, right? Like the senior boys one is like 13 pounds. Like and you know, it's awkward. So you just pick them up, set them on there, and you can go fetch the next one and mark and measure. Works pretty well. Okay, so that's like physics being applied to good use. Nobody gets their fingers or toes broken by a rolling shot put.
Well, unless you're standing on the track, like near where the incline plane is.
Yeah, but then that's your own fault.
I mean, yeah, that's called human stupidity. So.
Yeah, exactly. Okay, so if we're looking at this example here, okay, so we've got like a bobsled, okay, track, okay, and as they go down the track, we're obviously converting one form of energy into another, okay. So let's say that they just get in the sled. They don't push it like you normally would. They just get in the sled, okay. That would mean that all of their potential energy would be, or all of their mechanical energy, sorry, would be potential. As they go down the track, okay, some of that potential energy is going to get converted into kinetic because obviously as you go downhill, your speed increases, but your height decreases. So all we're getting is them turning into each other, okay, one goes up, the other goes down, until we get to the bottom where it's all kinetic.
So like a scale effect.
Yeah, exactly. Yeah, you always have the same amount of weight, all you're doing is moving it from one side to the other. Yeah. Now, this is a situation that actually occurred in Vancouver in 2010 with their skeleton track. Okay, so skeleton is luge for people who don't find luge exciting enough. Okay, so in luge, you get on the sled with your feet pointed down the track and you do this and you go down the track as fast as you can. For people who don't find that exciting enough, there's skeleton, which is luge head first. Okay? And unfortunately, one of the competitors during the practice runs, was killed because he went off the track. Okay? And the reason that happened was they got a lot more rain than they had anticipated, okay, at the facility, and it had lowered the coefficient of friction of the track below what they had ever designed it for. And by the time they got to the second corner, they were going so fast that the corner wasn't built to contain them. They never imagined somebody going this far up on the corner, and the guy was actually thrown because the corner was built like this, but it ended, that part of it, the overlap part ended, and he was still up there, okay? And so he was thrown out of the track and killed. So they're like, well, how do we obviously can't have people using this track, but we don't have another track, so what's the best solution to make sure people aren't going so fast here?
Brakes, more friction.
Can't change the friction because you can't control the weather.
It's like
Bigger wall.
Okay, can't build a bigger wall. The next day is the runs.
change the math.
Can't control that. Every athlete's different. You can't say, hey, you put some weight on, like for tomorrow.
Are you able to like double the, what are they called, like the skates on the bottom?
But you'd never let it. You'd never get athletes to agree to that.
That's just less high.
Less height. Yeah, they started them here instead. Simple physics solution, right? If the reason you're going off the track here is because of the amount of energy you have, don't let them have as much energy. Mass influences energy. Sure, if we could change the mass, that would be great, but you can't just say, okay, you got to drop 20 pounds for tomorrow. Okay? You can't, it's not going to work, right? Plus, the effect of losing the mass doesn't really matter in a perfect system because all things fall at the same rate. Okay? I mean, in the real world, it does matter, but all they did was start them lower. Okay? Then they couldn't be going as fast when they got to that point. Nobody went off the track again. Okay? Simple solution involving energy. Okay. All right. I showed you guys the Evel Knievel going over the...
No.
Yes, I did.
Yes.
Yeah, I did. Okay, so this is the law of conservation of energy. This is the law of conservation of energy version of the Evel Knievel jump, or Robbie Knievel jump, okay, over the Grand Canyon. So, I would like you guys to copy this one down. And we're going to walk through it together. Okay, so they're going to jump off of one side, the higher side, at 38 meters per second, 70 meters above the bottom of the canyon. When they land on the other side, they're only 35 meters above the canyon. We want to calculate how fast they're going when they land. All right, so I'll get you a chance to kind of write that information down, and then we'll walk through the solution. Okay, so because it says we ignore air resistance, we now know then that our initial mechanical energy and our final mechanical energy are equal. So it starts off EI equals EF. Okay? And then I would expand that out to be, okay, my initial potential plus my initial kinetic equals my final potential plus my final kinetic, because that's how you calculate mechanical energy. You add those two energies together. Now, what I'm looking for is VF. Which term is that part of? Yeah, my final kinetic. So I want to isolate this right now. Before I expand out any more, I want to isolate this. So what do I do with the EP final?
No, subtract.
Subtract, right. So basically what I'm saying is my initial mechanical energy, that's these two numbers added together, minus my final potential energy equals my final kinetic energy. That should make sense. Okay? All right. Can I expand it out now? Yep. Okay, so now I'm going to say m times g times h initial plus 1/2 mv initial squared minus m times g times h final equals 1/2 mv final squared. Okay. Now, what variable is in each term? Mass. So what can I do with it? I can cancel it for two reasons. It's in every term, so mathematically that's a rule. I can get rid of it. Okay. And secondly, we're ignoring air resistance. That means everything falls at the same rate regardless of its mass. So mass makes no difference in the final velocity of the motorcycle. So I can cancel it off. If you're not comfortable with that, you can put whatever number you want in there. Okay. On a test, I would give you the mass, just because it's happened once before where I didn't put the mass on a test, and I had people coming up to my desk, and they're like, Mr. Coderre, what's the mass of the motorcycle? And I was like, oh, 200 kilograms. Okay, and go sit down. And then another person came up to my desk. Mr. Coderre, what's the mass of the motorcycle? I couldn't remember what number I told the first person. 500 kilograms? And then there were people out there who realized that I had just given out two different numbers, and they're like, I forget it. I was like, then another person came up. What's the mass of the motorcycle? 1 million kilograms. It doesn't make any difference. You can plug in whatever number you want. It's going to cancel in the end anyway. Okay, so make it whatever you want. So I've got that. I want to get VF by itself, so I'll divide both sides by 1/2, and then I'll square root it. Okay, now I can plug in my numbers and get how fast the motorcycle is moving. So I'll have 9.81 times 70, that's my initial potential, plus 1/2 times 38 squared, my initial kinetic, minus 9.81 times 35, my final potential divided by 1/2. Now, this gets a little bit awkward on your calculator. So if you're not confident in being able to punch everything in or remember all the brackets and everything, you can do it piece by piece. Okay? It's entirely up to you. All right? What I usually do with a question like this is I actually do it piece by piece. I go 9.81 times 70. And then I go add that to 1/2 times 38 squared. And then I subtract 9.81 times 35. And then I divide that by 1/2. And then I square root. That way if I make a mistake, I'm only back one calculation. All right, so when they reach the ground on the other side, 46 meters per second. That's 166 kilometers an hour. Trying to hold on to that motorcycle would be like wrestling with an alligator at that point. Okay, like it would be really, really difficult. That's a big impact at that speed. Okay, did that look familiar?
Yes.
Okay, I hope so. Especially if you were in my class, because we only did about 30 of those. Okay, and you had one on your physics unit exam and one on your final exam. So I'm really hoping it looks familiar. Okay, all conservation of energy questions essentially work the same. All that's going to change is which variable are you solving for. You're either going to solve for initial height, final height, initial speed, or final speed. Those are the only four things you'd be looking for. Okay? So it's just a slightly different manipulation if you're solving for one of those. The rest of the setup is identical. All right. Okay, so that's what we just did. We can skip that. Okay, let's have you guys try 1 and 2 for now. Okay? I'll make them a little bit bigger here. All right, so with number 1 here, okay, it tells us it's an isolated system, so right off we know there's no work being done, okay, and that we can say that our initial mechanical and our final mechanical are equal, okay? So it says it's got an initial kinetic energy of 250 joules and a gravitational potential energy of 960 joules. The crate loses 650 joules of gravitational potential energy. What will be its final kinetic? What happens to potential energy in an isolated system? It can only be converted into what? Kinetic. The mechanical stays the same, right? Those two are part of mechanical. So if the system loses 650 joules and it's an isolated system, the only place it can go is from potential to kinetic. So all I actually had to do is take this number and add them together. Okay? That was the initial kinetic plus the amount of potential that was lost, okay, really converted into kinetic. So 900 joules would be our final kinetic energy there. Okay? All right, for number 2, we've got a mass of 55 kilograms, 225 meters above the ground, moving at 36 meters per second. Use the conservation of energy to calculate its velocity when it reaches a height of 115 meters above the ground. So, how many people have done number 2? Okay, I'll actually give you a little bit more time then. So this is another EI equals EF situation. Okay. So make sure you're getting this set up. Okay, what you're looking for is part of that term. Okay, so looking at number 2 here, right? The things that I know for number 2 are the mass, which is going to end up being irrelevant. I know the initial speed, the initial height, and the final height. So what I'm looking for is the final speed, which is part of EKF. So what I'm going to do is isolate that next, and I'm going to subtract EPF over to the other side. So this is the same as the Robbie Knievel example we just did. All right, so I'm going to have EP initial plus EK initial minus EP final equals EK final. All right, so that'll be M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals 1/2 MV final squared. All right, mass is in every term, so I can cancel the 55. Okay, I need to get VF by itself, so I'm going to divide both sides by 1/2. And then I'm going to square root both sides. Okay, so VF will be 9.81 times 225 plus 1/2 times 36 squared minus 9.81 times 115 divided by 1/2. Okay, will give me VF. So if you don't want to punch that all in like separate steps like I did in that first one, then you can do the bracket adventure. So that would be 9.81 times 225 plus 0.5 times 36 squared minus 9.81 times 115 divided by 1/2. I have too few brackets. I needed a third. See, there's where I messed up. I needed a third bracket at the beginning. Oh, and I can't hold it down. No, he can't hear it in his room. You could hear it in the prep room in between our rooms. But there's a room in between our rooms. See, and this is why you don't do it that way. Yeah, I'm sure it was the brackets, but no, let's do it this way. Okay, there it worked. So, it would be moving at 58.8 meters per second. I had too many brackets. Okay, when it gets to that point. Everybody all right with that one? Okay, now here's the one that's gonna make you think. So, I gotta make it a little bit smaller here because otherwise you can't see everything you need. So, we got a human cannonball, which is this thing they do at the circus, okay? And they shoot a person out of a cannon. And they go flying through the air and then they land in this net. So, the cannonball, human cannonball, is shot from a height of 15 meters. And they are moving at a speed of 21 meters per second at an angle of 20 degrees above the horizontal from a platform that is 15 meters above the ground. So, if the acrobat has a mass of 56 kilograms, what is his gravitational potential energy relative to the ground when he is at the highest point of his flight? To do that part, you will have to remember a little bit about projectile motion from the first unit, because you will have to calculate his velocity at that point. That would be his horizontal velocity, because what's his vertical velocity at the highest point? Right. So you just got to do one little bit, okay, to get his horizontal velocity, because remember, at his highest point, he has kinetic energy. He's still moving forward. Okay? And then, if the net, which he lands, is 2 meters above the ground, how fast is he traveling when he hits it? That one you can do right off the bat. You wouldn't have to do any projectile motion stuff for that one. Okay? That one you could do with just the information given in the question. For part A, you got to do one little trig thing, to do that. All right, I'll give you a few minutes on that one. So for number 3, for part A at least, you've got to do this little bit of trigonometry. It's shot, or the person is shot at 21 meters per second, 20 degrees above the horizontal. They're asking us about this point right here, where we know their vertical velocity is 0, but they're still traveling forwards. The speed they'd be traveling at forwards would be equal to the horizontal component of their projected velocity, because at that point they're not moving vertically, they're only moving horizontally. So what I've got to do here is calculate v horizontal, because that will act as my vf speed, final speed at that point there. So I'll take that cos of 20 and multiply it by 21 in order to get that speed. So cos of 20 times 21 gives me 19.7 meters per second. Now, it's a conservation of energy question. Okay, so I would have m times g times h initial plus 1/2 mv initial squared equals mg h final plus 1/2 mv final squared. The thing I'm looking for is the final height. Okay, so I'm just going to subtract the 1/2 mvf squared. So I'll have this ghi plus 1/2 vi squared minus 1/2 vf squared equals g times h final. I canceled the m's off already. Okay, divide both sides by g, and I'm looking at my final height. So that would be 9.81 times 15 plus 1/2 times 21 squared, because remember, conservation of energy uses speed, not velocity. So that 21 is how fast the guy is moving. Okay, so I can just use it without having to worry about the angle for that part. Minus 1/2 times 19.7 squared divided by 9.81. Okay, so when I do that, I should get, oh, they just want the potential energy at that point, don't they? Okay, well, that's fine. Yeah, that's fine. We still need the height for that, so we'll just calculate the height. So 9.81 times 15 plus 0.5 times 21 squared minus 0.5 times 21 squared, nope, 19.7 squared.
You dropped right.
No, I have a minus in there.
Oh.
I don't know what that's for. Delete. And divided by 9.81. All right, so he's only 2.6 meters higher at that point. If I want to calculate his potential energy, I take that number by 9.81 times, what was it, 56? Was their mass? Okay, 9.69 times 10 to the 3, I'm getting the same number. Well, I get 9.68, but okay, close enough.
So what was the value of that 17.6? Sorry, that was your final height?
That was my final height.
Okay, and we multiply it, yeah.
Yeah. Okay, and for part B, you guys can do that. It's basically this. You're just calculating its VF now. You can use the 21 for its VI. All right, give you a few minutes to get ahead of me on that one. So the only real trick to that one was this extra piece of trig. Okay, that was it. Yep. Okay, now a pendulum is another example of the law of conservation of energy. And what is it? Oh no. I've lost my we can use it Okay. So A pendulum, and we'll actually talk about this quite a bit in Unit 4 as well, okay, is a perfect example of the law of conservation of energy. Right now, this is at the lowest point in its arc. Would you agree? Okay, so in terms of what this thing can do, does it have any energy right now? No. I mean, yes, it's above the ground, but it can't fall. This is the lowest point, okay? Does it have energy now?
Yes.
What kind?
Potential.
And? Mechanical. Because it has potential, it has mechanical. If I let it go, gravity will accelerate it, okay, along that arc back down to this position. So when it goes through that position, when it's actually swinging, it would only have kinetic at that lowest point. All of its potential would turn into kinetic as it swings back and forth. All it's doing is constantly converting potential into kinetic. Okay, perfect example of the law of conservation of energy. Okay, just going back and forth, back and forth. Everybody with me there? Okay. All right. I would like you guys to try the question here about the model rocket. Let's write down what we know first. So we know the mass, not that it's going to matter, but we know it. So 3.00 kilograms. It's fired so that when it's 220 meters above the ground, it is traveling vertically upward at 165 meters per second. At that point, the fuel runs out. Okay, at that point, it then has all the mechanical energy it is going to have for the remainder of its flight. So those are our two initial values. Okay, our initial height is going to be 220 meters, and our initial speed is going to be 165 meters per second. Okay, assume the effective air friction is negligible and that all potential energies are measured from the ground. Okay, what's the mechanical energy of the rocket relative to the ground? Okay, how do I calculate mechanical energy? EK plus EP. All right, so to do that one, I'm just going to do this. M times G times H initial plus 1/2 MV initial squared. Okay, that will get me my mechanical energy. So for this one, sorry, that'll be 3 times 9.81 times 220. I have to include the mass here. Why?
Because you don't divide it by the mass.
Well, I don't divide it by the mass, but they're also asking for the energy. They're not asking for a height or a speed where mass is irrelevant. In energy, mass is relevant. Mass is one of the things that affects how much energy you have, so I don't cancel it here. Okay, plus, sorry, that's supposed to be 220. Okay, and then 1/2 times 3 times 165 squared. So 3 times 9.81 times 220 plus 0.5 times 3 times 165 squared. All right, so there's my energy, my mechanical energy, 4.73 times 10 to the 4 joules. Okay, that's my mechanical energy at that point, and everywhere else.
How come the S from 1 is different on A?
Because it's question 2.
That's what threw me off.
All right, we'll talk some more about that tomorrow. You will have a quiz tomorrow.
On what?
On work energy theorem, because we haven't had one that counted for marks. All right, so for part B, okay, we got EI equals EF. Okay, we know energy is conserved here. We don't have to do any of that projectile motion stuff we had to do in part A. Okay, we're just going to go EP initial plus EK initial equals EP final plus EK final. What we're looking for is part of the final kinetic, so we'll subtract the potential over, and we'll have this M times G times H initial plus 1/2 MV initial squared minus MGH final equals 1/2 MV final squared. Okay, the M's will cancel in this case because I'm not looking for a type of energy. I'm looking for the speed, which is not dependent on mass. Okay, divide both sides by 1/2, and square root, same as we did for all the others. Okay, so VF will be 9.81 times 15 meters plus 1/2 times 21 squared minus 9.81 times 2, because they're still 2 meters above the ground when they hit the safety net, okay, divided by 1/2. Okay, when we do that, we should get 26.4 meters per second. Okay. All right, questions on that one? Okay, that would be a very typical one to get on a test. Part B, not part A.
Pretty high at Canada.
Yeah, 15 meters, yeah.
I'm not on the ground, I heard that it's 150.
All right, questions there? Okay. Now, for a pendulum, okay, okay, so for the model rocket, if I want to calculate mechanical energy, do I need to use the mass? I do, okay? So if I take the mass and I've got the height, the initial height and the initial speed, can I calculate the initial mechanical energy? Yeah, okay, I just have to do this. Mechanical energy equals potential plus kinetic, okay, and just go m times g times h initial plus 1/2 mv initial squared, okay, so 3 times 9.81 times 220 plus 1/2 times 3 times 165 squared. And when I do that, I should get like 4.73 times 10 to the 4 joules. Is that the mechanical energy only there? No, that's the mechanical energy everywhere. Okay, so that means when it reaches the highest point on its trajectory, what will the gravitational potential energy be? That number. Why?
It's not losing energy.
Yeah, and a rocket goes straight up. So when it's at its highest point, this rocket, because it does say straight up, okay? Vertically upwards. So when it's at its highest point, it doesn't have any kinetic energy. All of its potential, okay? The rest of them you have to do a bit of calculating for. We'll look at that at the start of tomorrow's class. You will have a quiz tomorrow.
Yeah.
Okay, because we haven't had anything on work energy theorem, so you will have a quiz on work energy theorem, which will be posted shortly.
Rockets do not